Now, welcome everyone. It's week 6, Trinity term 2021 of the Oxford Philosophy of Physics seminar. This week, I'm very pleased to welcome Jacob Barandes from Harvard. Jacob's a lecturer in physics, in fact, but a researcher in the philosophy of physics these days. He's also a faculty affiliate with the Harvard Black Hole Initiative and founder and organizer of the Harvard Foundations of Physics Workshop Series. His work encompasses foundations of quantum, classical limit, field theory, general relativity, thermodynamics, and formal methods in mathematical physics. And his more recent work has been with, for example, David Kagan on a minimal modal interpretation of quantum mechanics, and his most recent paper, just out this year in Foundations of Physics, is on a classical analog of the Wigner classification of particles as irreps of the Poincare group, specifically for massless particles. But today he's going to be telling us why we shouldn't believe in Hilbert spaces anymore and give the case for Platonic quantum theory. So take it away, Jacob. Thank you very much for being here.
Thanks so much, Adam. Thanks to everyone who's organizing this seminar series. It's been a real joy to participate, especially in these times. And thanks to everybody for coming. All right, so this is a bit of an ambitious talk. I'm going to go somewhat quickly. So let's get started. Right, so the title of this talk, Why We Shouldn't Believe in Hilbert Spaces Anymore. It's a bit more of a provocative statement than it is maybe warranted, but I'll get to the subtleties later, and the case for a different interpretational approach to quantum theory. I have here a reproduction of a part of a letter from von Neumann to Garrett Birkhoff from 1935. And I'll make reference to this letter a little bit later. All right, can people see my mouse pointer? Great, okay. All right, so the outline of this talk will be some introduction, motivation. We'll talk about the classical case and then the quantum counterpart. And then I'll talk about the measurement process, both classically and quantum mechanically, and then we'll move on to the conclusion. So I'll start with the introduction. All right, so this I think people know, right? Quantum theory, very empirically successful, but still no consensus over its proper physical interpretation. As part of this talk, I will argue that the historical foregrounding of the Hilbert space picture has been a mistake when it comes to trying to interpret the theory. This is not to say that Hilbert space pictures are not unbelievably mathematically useful and that we shouldn't keep using them. We absolutely should. But in particular, I'll argue that Hilbert space pictures are in some ways analogous to gauge pictures for classical field theories or phase space pictures for classical mechanics. They're mathematically useful, but interpretationally obscure. And in particular, they're not where we should start when looking for an ontology. Imagine if Newton had been handed the phase space formulation as the starting point for classical physics with all these canonical transformations. It would have been very difficult to figure out where to get a grapple on the ontology. This is the von Neumann quotation. I would like to make a confession which may seem immoral. I do not believe absolutely in Hilbert space anymore. Now, von Neumann, what he was thinking about was generalizing classical logic to quantum logic and trying to think about quantum mechanics from the standpoint of a new logical framework. This is not the direction I'm going to take, but I still take some inspiration from this quotation. Since about 2017, I've become increasingly interested in the Gelfand-Neymark-Siegel construction, the GNS construction, both for foundational and also pedagogical reasons. I first got interested in this in trying to teach quantum mechanics to students with very little background in the subject. And if I have some time, I'll talk a little bit about why I found that approach helpful. Roughly speaking, with the GNS construction, and many of you already know about this, but some don't, what it implies is that when you have enough starting ingredients, the Hilbert space picture emerges more or less automatically. If you consider how bizarre and difficult to interpret wave functions, self-adjoint linear operators, and so forth are, particularly in that light, the GNS construction suggests that maybe we shouldn't read too much into those ingredients. Hilbert space picture is not wholly writ. It's a paradigm. Perhaps it's akin to the shadows on the walls of Plato's cave. And in that analogy, the GNS construction is like the fire that produces those shadows. This is actually where the name of this interpretation, Platonic interpretation, comes from. Relevant mathematics here is C-star algebras. Many of you know about this, and some of you don't. That's okay. I'll review what we need to know. These are widely used in algebraic quantum field theory, also by some philosophers of physics and mathematicians who work in functional analysis. I will say they're almost unknown in most of the physics community. I can say that relatively confidently. This is a bit of a complicated slide, but I wanted to fit it on one slide because this is a summary of the interpretation. This is the whole thing on one slide. The basic idea is that we're going to start, and I'll go into more detail about how all this works, but just to summarize, we start from the get-go with a statement about what the ontic stuff is of our model. These are ontic properties of some kind. If we're thinking about mechanical particles, these could be positions and momenta for fields, intensities, and rates of change. Then we encode these ontic properties, potentially with some coarse graining for convenience, into a corresponding set of random variables. Already at this level, we've introduced some mathematical abstraction for mathematical convenience. Random variables have individual statistical distributions, but we'll see that in the quantum case, there are also subtle interrelations between these ontic random variables. And then what we'll do is encode all of that epistemic-statistical-nomic data into a set of things called state maps that will capture all that information. With these ingredients, we'll be able to build a C-star algebra, and I'll explain what that is. This is, you could think of it as a convenient software layer. And then once we have a C-star algebra, the GNS construction generates a Hilbert-space picture as a higher level software layer with an additional level of abstraction. I almost think of this almost an analogy with you start with Newtonian mechanics, you introduce Lagrangian mechanics, then you introduce Hamiltonian mechanics, then you introduce the Hamilton-Jacobi formulation. You keep stacking abstractions on top of each other. So what are the key takeaways? One is, I'll argue the Platonic quantum theory is a conservative interpretation with one world, with a non-perspectival notion of ontology. This is not to say everything is non-perspectival, but I'll talk about exactly what is and what isn't. From this standpoint, neither C-star algebras nor Hilbert spaces are regarded as fundamental or even unique. We allow that some familiar features of classical probability can break down. Got to bite the bullet somewhere, and I'm going to bite it there. In particular, joint probability distributions will only be assumed to exist in special cases, and I'll go in detail how those work, in particular when we talk about the measurement process, in particular when there's no direct entanglement between relevant ontic properties, which is a novel statement about when joint probabilities should or should not exist. From this standpoint, decoherence is a physical process, whereas collapse of wave functions or what have you is a subjective perspectival thing. We also bite the bullet on non-locality, as I'll explain. But one of the key motivations of this approach is to do something along the lines of what Jaynes asked for in a contribution to a set of essays in 1989. And he said, our present quantum mechanical formalism is not purely epistemological. It's a peculiar mixture describing nature, realities of nature, incomplete human information, all scrambled up by Heisenberg and Bohr into an omelet no one has seen how to unscramble. The people who work in cubism particularly like this quotation. The Platonic interpretation is a different way to try to unscramble this quantum omelet, in particular by separating off the ontic sector of quantum theory from basically all the other stuff, the epistemic-statistical-nomic stuff. The ontic sector will be those ontic properties, and the epistemic-statistical-nomic sector will be basically everything else. Okay, so that's the introduction. Now, motivation. So what do we do in classical physics? Well, generally we take a physical system, we regard it as existing in some sense in 3D space, consisting of material bodies moving along definite trajectories or field intensities varying in strength at localized points. This neglects subtleties that arise for gauge theories, but more on that later. And this is a particularly nice picture for attaching ontologies to. In fact, usually what we do is we start with the ontology and then we layer mathematical description on top. In quantum theory, we start from traditionally textbook quantum theory, the Dirac von Neumann axioms. These paint a far murkier picture of reality. At a kinematical level, the description of what the ingredients are. Well, all contingent facts are supposed to be encoded in a mathematical state vector in a Hilbert space over the complex numbers equipped with an inner product. For dynamics, there's supposed to be a Hamiltonian operator for which state vectors evolve according to the famous Schrodinger equation. And there's trouble right away for open systems. And you all know this, but in a undergraduate introductory textbook, usually this isn't treated right away. But for open systems, as most of you know, it is systems that can exchange information with environments. You get entanglement between the system that you're looking at and the environment or apparatus or whatever it is that's studying the system. This leads to a failure of factorization between that open system and its environment. And open systems generically don't have state vectors. Instead, we have to use a density operator. And generically, density operators in contact with an environment evolve according to a much more complicated master equation. Like the Lindblad equation is a simplified version of this if you assume Markovianity and you assume homogeneity in time. But more generally, you get a much more complicated master equation. And these generically lead to ever more entanglement with the environment. The connection to empirical results makes the story even murkier and more complicated. In the simplest case, each observable feature A of a quantum system corresponds to a self-adjoint linear operator. The possible measurement results correspond to its eigenvalues. Here, I'm labeling the eigenvalues with some label lowercase a that distinguishes them. For a system described by a state vector, as you know, we let ket psi a be an eigenvector of A. We can introduce a projection operator. It's this ket bra construction. And then we can compute the associated probability of getting that measurement result as an inner product or by sandwiching the corresponding eigenprojector in the state vector. And observables more generally have expectation values that are expressible in this famous way. For a system described by density operator, we generalize a little bit. We work with traces. We multiply density operator by projector and trace to get the probability. Or to get expectation values, we multiply the operator in question by density operator trace. If a ket vector has unit probability for a measurement of A to yield a specific result, it's definitely going to get the results, a particular result for the observable A with probability 1, then the ket's supposed to be an eigenvector of that operator with that eigenvalue. This is the famous eigenvector-eigenvalue link. Immediately following the measurement, the state vector or density operator collapses to that definite eigenvector, assuming an idealized measurement. This ensures robust results under repeated measurements. If we measure again quickly before we let any time evolution happen, we're guaranteed to get the same result again. An important example, if Q represents a classic light configuration, like a particle position or a bosonic field intensity, well, the system has some state vector. We associate a wave function to be these inner products of the state vector and the eigenstates corresponding to that observable, or equivalently the coefficients in an expansion of the state vector in the coordinate basis. And then the absolute value squared of the wave function gives you probabilities or probability density. These wave functions naturally live in configuration space. For these systems, that configuration space looks a lot like what you think of as the classical configuration space. For n particles in 3D, it would be a 3n-dimensional configuration space. So what's the measurement problem? Well, there's like a million ways to phrase this. One way I like to think of the measurement problem is, on the one hand, we have standard time evolution, Schrodinger equation for a closed system, or some suitable master equation for an open system, but neither of these singles out a definite measurement result. Whereas when we have collapse after a measurement, we get a definite result. One problem is the Dirac-von Neumann axioms don't rigorously define what is an observer, what is a measurement. Just measurements are things that observers do. And that's a problem. There's this ambiguity built right in. Now, decoherence can't save us here. Decoherence is the tendency of environmental interactions to make the density operator of a system evolve rapidly into a form that resembles a classical probability distribution for specific observables. The problem is this doesn't single out definite measurement outcomes. And it doesn't work. In fact, decoherence increases the level of entanglement with the environment. But from time to time, you see people try to argue that you can somehow make measurements happen through some sufficiently sophisticated decoherence process. The problem is that collapse, when it happens, looks at the level of Hilbert-space as like some non-local event. Whereas decoherence, if it's working under local Hamiltonian or a local quantum channel or something like that, it can only produce local effects. And this is thanks to the no signaling, no communication theorem. So there's like a fundamental problem here. All right, so an interpretation of quantum theory should resolve, ideally, this measurement problem, among other things. It should ideally also have some kind of ontology, which I take to be part of the objective structure of the interpretation. This is what exists supposedly in reality. It should have some epistemology, which may combine objective and subjective elements, chancy and uncertainty type elements. This is what we can know, what we do know, what probabilities we can assign to things that we know or don't know. And again, there could be objective limitations. It might not just be a matter of our subjective ignorance. And there should be a nomology, which can entail both objective and subjective features, as I'll explain in a moment. These are the laws that summarize or govern, depending on one's attitude toward laws, the behavior which could potentially be statistical with the ingredients of the theory. I have an analogy here that will be important, just to raise, attention to a couple of subtle details here. So let's talk about nomology for a second. Consider the sequence of numbers 1, 4, 9, 16, 25, 36, ... We'll call this our ontology. If you want, I've got a bunch of rocks sitting in front of me, and I've got 1 rock and 4 rocks and 9 rocks. Or I have rocks that change in number as a function of time. I don't know. It seems like there's objectively a pattern here, especially if when you check, the next numbers happen to be 49, 64, 81, and 100, setting aside the problem of induction. And this is not going to be one of those trick questions where it turns out this is some sequence that after the 15th number becomes something totally different. I'm not playing any games here. You look at this and you go, well, I'm going to posit that there's a law here, a nomology that summarizes or generates this pattern. It's the sequence of square integers. But then someone else comes along and says, no, that's not the law. The law is that we're adding consecutive odd integers. Well, who's right? It doesn't make sense to ask who's right. That's not a meaningful question. These two laws are mathematically equivalent. The pattern is some unique thing, but laws that describe it are not unique. There can be a many-to-one relationship between nomologies and patterns, and that's okay. We'll see this arise again a little bit later. So some prominent interpretations and approaches, and I apologize right now because many people here may have attachments to some of these, and this is a super superficial summary, and I apologize, and if I'm mischaracterizing it because of this, I apologize in advance. To the extent that there's anything like a Copenhagen interpretation, there's some notion of microscopic versus macroscopic systems, and when classical macroscopic systems interact with quantum systems, you get collapse, and there's a vague notion of a division between the two kinds, a Heisenberg cut, but where is this? What is the meaning of an observer, and so forth? In de Broglie-Bohm or Bohm mechanics, and I'm collapsing the two together, I know that there's subtleties between them, and there's different flavors of them, but here we supplement the standard formalism of quantum theory with ontic hidden variables, particle positions, bosonic field intensities. There's a problem with fermionic fields, which I'll come to a little bit later. But here the ontic random variables are traditionally read off of the configuration space of the system, or from the domain of the wave function. Now, there are other approaches to this, but this is the more traditional approach. We then regard wave functions as ontic pilot waves, or not as ontic at all, but as nomology, sort of like Hamiltonian, that govern how the ontic hidden variables behave. There are major problems, as we all know, with relativity at varying levels. There's also trouble with systems that don't seem to have configuration spaces in any familiar sense, like fermionic fields, and I'll come back to those later. Then there's the Everettian approach. We shrink or expand, I guess, the ontology to a universe, to the universal wave function. Although there are many different flavors of this. There's space-time local realism, where you're attaching ontologies maybe in some local sense. Again, this is a very stripped down version of the story. The nomology is shrunk down to the Schrödinger equation in some flavors, but not in all. And then the idea is that the familiar world or worlds or our experience emerges in some branched way, globally or in local patches of space-time through some emergent process. Traditionally, there's been a lot of contention about the emergence of probability from this approach. I would argue that if you're going to derive probability deductively, well, then it's got to be inherent in your premises. If you're going to derive it inductively, well, inductive reasoning, it already includes in a notion of probability. But this is a much larger discussion we're not going to have here. So I'm not going to say much more about the Everett approach. I'm going to leave it here. There are other approaches, spontaneous collapse. There are quasi-instrumentalist approaches like cubism. I'm not going to say much more about this, except to say that in quasi-instrumentalist approaches, you run into this question of, well, if you've got probabilities, what are these probabilities of? And the moment you say what they're of, you're saying something and suspiciously ontological, and that's an area of tension. I would argue that all these interpretations and approaches appear to take the Hilbert-space picture as fundamental, but Hilbert-space pictures are fickle. I'm going to set up an analogy here, so bear with me. So recall classic electromagnetism. We've got the Maxwell equations, there they are. We've got our physical fields, the E and B fields. but it's often mathematically very convenient to introduce gauge potentials. The phi and A fields, we can express the E and B fields in terms of them. This gauge picture is metaphysically murky. Phi and A are radically non-unique due to the theory's invariance under gauge transformations. I can replace phi and A with new gauge potentials under this transformation where lambda is an arbitrary function of spacetime. So what do? Well, we regard the physical and maybe, if you want, ontological sector of the theory of classical magnetism to be its gauge invariant content, to be the stuff that's gauge invariant. This includes E and B, it includes fluxes. If you include a little bit of quantum, it includes, Arne-Bohm type phases, which are gauge invariant. But I'm gonna take this a couple of more steps. So some of you may know that you can encode the Maxwell equations into a Lorentz covariant formalism. We stick the E and B fields into this anti-symmetric rank 2 4-dimensional tensor, the Faraday tensor, which can be expressed in terms of a 4-vector gauge potential, a gauge connection, as it's called, which has connections, no pun intended, to some interesting constructions and fiber bundles and different geometry that we won't have time to talk about. But all of the 3-dimensional variables are encoded into this Lorentz covariant formalism. We have a current density, and then we can express the Maxwell equations in this way. Gauge transformations now take this form with the gauge connection transforming by the addition of a 4-dimensional spacetime derivative of an arbitrary scalar function. This is actually a special case of a more general construction. This is the most technical slide. I apologize for its technicality. But if you're given a collection of mutually interacting massless vector fields, not just the electromagnetic field, but cousins of it that can all mutually interact with each other, they all carry charge under their own interactions, there's a mathematically consistent way you have to put it together, and that's as a non-abelian or Yang-Mills field theory. There is some Lie group associated with this field theory, some symmetry. The theory needs to be consistent. The symmetry has matrix generators. We stick the matrix generators in with the fields and define matrix valued fields. So these look like A mu, they look like the gauge potentials we had before, but they actually take matrix values. They're non-abelian, they're non-commutative. That's where the non-abelian comes from. We introduce a generalization of the derivative called the gauge covariant derivative, given by this formula. We introduce a generalization of the Faraday tensor, which can be expressed in this way in terms of the gauge covariant derivative. And then with the theory, the gauge invariance we had in the case of E&M is generalized to a transformation where certain objects like the Faraday tensor transform by conjugation, by a local unitary transformation generated from our Lie algebra, and gauge connection transforms in a more complicated way. Rather than just VA V dagger, we get VA V dagger minus this inhomogeneous piece. And these are homologous, if you go back a slide, to the two pieces you see here. In the abelian case, electromagnetism, A mu doesn't get a V dagger, or if it does, it's like a 1-by-1 phase factor that cancels. And then the second term is this derivative term. This sort of more complicated construction you see here is a generalization of that derivative term. And this can again be expressed directly in terms of the gauge covariant derivative. These transformations leave the physical ontological sector of the theory invariant. They're very useful, especially if you want to quantize this, write down a path integral representation, do standard model physics. This is almost unavoidable. So Harvey Brown had a really beautiful paper in 1999 that had a big impact on me. And he begins the paper by talking about the appearance of a very similar kind of gauge invariance in quantum mechanics. You can take the Schrodinger equation, the standard Schrodinger equation, and rewrite it in this way in terms of a gauge covariant derivative with a Hamiltonian playing the role of a gauge connection. And then the Hilbert-space picture has a non-abelian gauge invariance completely analogous to the case of a Yang-Mills theory. In fact, the formulas are identical. This transformation leaves the Schrodinger equation unchanged in form, and it preserves probabilities expectation values. This is the gauge invariant content of quantum theory. And I would argue that this means that's where we should be looking for our ontology, not the level of the Hilbert space, which from this point of view is more akin to gauge variables. Right, so, this is just summarizing what I just said, but matters are even worse. You can take a complex Hilbert space and replace it with a real Hilbert space by introducing a single so-called universal qubit. These are just the details, but you introduce some orthonormal vectors for the qubit. Any operator can be written as its real plus its imaginary part. You can take the imaginary unit and write it as a 2x2 matrix once you've adjoined this universal qubit. And you can rewrite this as a tensor product with this I state and the complex conjugate of a tensor product with this other state. And it turns out this leaves all the predictions of quantum mechanics completely unchanged as long as you slightly renormalize the Born rule. The only downside is that the formalism ends up looking a little more non-local than it did before. And that's the substance of this paper by Renou et al. They have a paper on the archive from this year where they argue that real quantum mechanics looks a little more non-local than it would otherwise. But fine, I mean, Coulomb gauge also looks superficially non-local in terms of gauge variables, but doesn't bother us. There are worse ways we can, there are other gauge choices we can make. If you've got a quantum channel and you're unhappy that it's not a unitary operator, you can adjoin an additional quantum system with its own Hilbert-space K and make it look unitary. There are other gauge choices. When I teach QFT, I like to start with a single particle Hilbert space, enlarge the Hilbert space, drop the requirement that the inner product is positive definite, and this turns out to give a very elegant Lorentz covariant way to describe particles, massive and massless particles of arbitrary spin, and then you get back to the physical states by projecting down, or if need be, quotienting this larger Hilbert space. So Hilbert spaces they're very manipulable. They're very, I would argue, flimsy and non-robust. So at this point, I'm reminded of a famous painting, Rene Magritte, The Treachery of Images. The famous pipe, how people reproach me for it. And yet, could you stuff my pipe? No, it's just a representation. Is it not? So if I'd written on my picture, this is a pipe, I'd have been lying. With apologies to Magritte, this is not a state. All right, so what am I going to do the rest of this talk? I'm going to argue we can derive quantum theory from a sharp ontology consisting of physical systems with basic properties, but that exhibit a non-trivial probability structure, and this leads to this new interpretive framework. So there'll be an ontology, states characterized by ontic properties. There'll be an epistemology, interdependent probability distributions, that capture the degree to which those underlying ontic values are manifest in the external world. And you can take a chancy, frequent dispropensity, best systems, whatever approach you want to probability. I'm not going to solve the probability of this talk. I'm going to bite off one problem at a time. And then there's a subtle but ultimately codifiable collection of rules for those ingredients. That's the nomology. Let me just say a word about this notion of manifestness. So Schrödinger said, I think rather beautifully in his paper, this was the Schrödinger cat paper, that there's a difference between a shaky or out of focus photograph and a snapshot of clouds and a fog banks, right? The picture can be sharp of something blurry, or the picture can be blurry. In the Platonic interpretation, the underlying ontology will be sharp. It just won't, it'll be blurry. In terms of its availability, its manifestness to the outside world. This means that epistemology from this point of view is not a wholly subjective thing. It has an objective aspect. There's only so much that nature will allow us to know about certain underlying properties, and those properties can exhibit a non-trivial statistical behavior. In a sense, we're shifting in the Platonic interpretation of the weirdness from the ontological sector over to the epistemic-statistical-nomic sector, as I'll explain. All right, so what obstructs full manifestness of a system's ontology? Well, there are a lot of things. But the key new idea, as I said before, is that ontic properties generically will not share a meaningfully correct overarching joint probability distribution outside of certain special cases that have to hold at least to a good approximation. The corresponding observables have to have commuting operators, and there has to be negligible direct entanglement between them. That second property is new. After a measurement process, we'll see that these conditions will be satisfied to an incredibly good approximation. And so it is in that case that joint probability distributions between measurement results and pointer variables will emerge. Not the ontic properties themselves, which are always there, but their statistical correlation will emerge. And that will account for definite measurement outcomes. So from this point of view, again, the Hilbert-space picture is a convenient tool, software layer, not assumed to be a fundamental aspect of reality. Okay, let's talk about the classical case. And this will be a motivation for what we're going to do in the quantum case. So what is the ontology of the classical system? Well, you could have different opinions on this, but a flat-footed attitude toward ontology is classical system has got properties that define the system's ontology. It could be particle locations and momenta, whatever you want. Each of the system's mutually exclusive states of ontology, ontic states, which I'll label as x, x prime, x double prime, these are different ontic states, specifies once you have one such state, it determines values of all those properties. And there could be some possible coarse graining here as convenient, maybe even into discrete possibilities, like a coin flip being heads or tails. So examples, mechanical systems of particles, systems of fields, and so forth. All right, practically speaking, we don't always know the values of those properties with certainty. So, our epistemic state, our epistemology, is captured by an overall probability distribution. We associate probabilities with those ontic possibilities, those ontic states, and this means the ontic states form a sample space for some probability distribution that obey the standard Kolmogorov axioms that are listed here, positivity, sum to one. At this level, it's convenient often to associate each ontic property with a symbol that stands for the list of its possible real values that are determined by the underlying ontic state, x or x prime or x double prime. And these have probabilities given by the epistemic state. In that case, we call A a random variable. We can define algebraic combinations of random variables, a plus b, a times b. In general, a function of random variables is defined for a given ontic state x to be whatever the corresponding formula is when you plug in the values of the individual random variables. In this case, our collection of random variables is said to form an algebra. It's a set of things you can add together, you can multiply them together, you can multiply them by real numbers, and so forth. They form what's called an algebra. To each ontic state x naught, we can associate a particular random variable, p sub x naught. This is a projector. It's just a true or false question. The system's ontic state is x naught, true or false, with 1 for true and 0 for false. So its values, when you plug in a particular ontic state, are just a Kronecker delta function. It's nilpotent. If you square it, you get 1, because 1 squared and 0 squared are both 1. And we call this an elementary projector. Elementary projectors obey mutual exclusivity. If you sum them over all the ontic states, you get the identity. That's I, the identity random variable. It's always true. It's always 1. And for all of the random variables A, we have an eigenvalue equation when they act on these. And we can also expand any random variable as a linear combination of these elementary projectors, with the eigenvalues of the observable appearing as the coefficients. Given subsets of a sample space, omega, subsets E and F, we can introduce generalized projectors to be a sum of the projectors corresponding to all the points in the two subsets E and F. These automatically have the property that when you multiply them, you get the projector onto the intersection. Notice, set theoretic intersections are commutative. And this is compatible with the idea that these projectors should be commutative, which they are. We can introduce complex valued random variables for convenience. It's often very nice to have complex variables available. And then we can introduce an involution, a star operation that just replaces z with a plus ib with a minus ib. We call that a star operation. Or in terms of ordinary complex conjugation, once you plug in an ontic state, well, then this is just an ordinary number, and then star just gives you the complex conjugate of it. We can introduce a norm to be the supremum among all of those absolute values for a given random variable. And we can use this to introduce notions of limits and continuity and topology. If we extend our algebra to make it closed by including all limit points of Cauchy sequences and other sort of technical assumptions that are very convenient, we now have what's called a C-star algebra. C stands for closed in the sense of topology, from including all of these limit points. And the star is the star. So, given an epistemic state that assigns probabilities to ontic states, that's now equivalent to introducing a so-called state map defined on the C-star algebra itself. Omega is a state map. When you act on an element of the C-star algebra, it just spits out the expectation value. If you act on the element of projectors, it gives you the individual probabilities back. Let S be the set of all those state maps. We can get joint probabilities from state maps. You just plug in the product of your two projectors, and it will give you the joint probability for both of them. You can introduce covariance, standard deviation. All of these can be expressed directly in terms of state maps. You can even re-express the C-star norm itself in terms of these state maps. The C-star norm can be expressed as the supremum among all the states, all the state maps, the square root of omega z star z. So this gives a nice, convenient way to express everything in terms of the state map. When you have a C-star algebra and you have a state map satisfying these basic desiderata, which are satisfied by our classical state maps, and you require that the norm given in this way is a C-star norm obeying the usual requirements, then the GNS construction swoops in and says, you've got a Hilbert space. The state map corresponds to a state vector. Classical random variables correspond to, in this case, commuting operators, in the classical case. And expectation values can be expressed by sandwiching the operators in the state vectors. Look familiar? That looks awfully familiar. So key lessons. Hilbert spaces need not be regarded as fundamental aspects of reality, at least in this classical case, although they may be convenient for calculations. Some of you may know that there is actually people do this. It's called the Kutman von Neumann formulation. There was just a workshop a couple of weeks ago that I participated in that was just devoted to the Kutman von Neumann formulation. And it's useful for studying dynamical systems, for chaos, for the classical limit, but even for purely classical purposes, it's useful. It makes it easy to derive lots of fun formulas. This is a super quick way to derive the famous formula that the correlation coefficient of two random variables is between -1 and 1. It follows, directly from this formalism. You can get it directly from the Cauchy-Schwarz inequality. It's a very cute way to derive this. But the Kutman von Neumann formulation contains a lot of weird ingredients, strange non-ontic ingredients. You can introduce non-commuting operators. You can do all kinds of bizarre stuff. But we just don't read a lot into that because we know. We don't start with the Hilbert-space picture. The Hilbert-space picture is a clearly derived higher level software layer. And so we're naturally suspicious about attaching too much meaning to it. Now let's talk about quantum theory. So to begin moving to quantum theory, we're going to generalize the classical case. We're going to drop the assumption that ontic states form a valid sample space. This doesn't mean there's no ontology, there are no ontic states. It just means to be a sample space, you have to assume there's a well-defined joint probability distribution, and that's what we're not going to assume is true anymore. And this is a matter of epistemology. I'm not saying the ontic states aren't there. I'm just saying that nature is limiting what we can know about them, and in particular doesn't let us assign them a joint probability distribution in general. Now, system still has ontic random variables representing possible underlying values of an ontic property. That you can still do if you want. There could be some coarse graining here. Let's suppose we pick some ontic property. We say the system has some ontic property A, and I represent it with a random variable. Well, it'll have some list of possible values. Those will make up its own individual sample space belonging just to A with its own associated set of probabilities. I can define projectors in exactly the same way. This is a carbon copy of an earlier slide, but this is just for that one random variable A. Given a second ontic random variable, their individual probability distributions may now be incommensurable, which is connected to the failure of the overall set of ontic states to necessarily be a sample space. There may not exist a physically accurate joint probability distribution that reliably describes the current underlying values of both A and B, and that yields the individual probability distributions by the correct marginalization formulas. That's strong constraints, and I'm just saying maybe it's not always true. Could be subtle interdependencies between the two probability distributions, so that physical effects, or trying to uncover one of them or pin one down, affects the other. There's already hints here, the uncertainty principle, entanglement, and incompatible observables, but this is just at the level of looking at random variables. If there's no joint probability distribution for A and B, and this is crucial, then A plus B and A times B and other such algebraic combinations are not random variables. They're not, because there's no probability distribution for them, because I can't assign them probabilities anymore. This doesn't say that there aren't underlying values for A and B, just that they're not going to be captured in a well-defined joint probability distribution. Right. So again, not a matter of ontology, it's just a matter of what can be known, what nature is letting us know about these things. I can still define a formal algebra. I can still talk about A plus B and A times B and just regard them as formal things. And I can introduce formal state maps that take this formal algebra and map them to the real or complex numbers, with the condition that if I plug in an ontic random variable, A, then I'm getting the expectation value. Okay. But the complex numbers associated to A plus B and A times B by the state map, they don't have a clear, obvious interpretation. They're encoding something. It's not clear what they are. We'll see that they encode detailed interdependencies. Now, our choice of set S of state maps is now really crucial, because for a given choice, it may be that certain combinations like AB always give the same result when you plug them into an arbitrary state map with anything else as maybe BA plus C. And if that's true, if our set of state maps has this feature, that for all things you plug in, AB is always gives the same result as BA plus C, well, then we can say that our algebra effectively has a commutation relation. AB equals BA plus C, or AB minus BA equals C. So in this way, a particular choice of set of state maps, which again encode epistemic information, laws, they dictate a particular algebraic structure on the formal algebra. Once we quotient out by these relations, we get commutation relations, whatever algebraic relations we expect. But these are coming from our choice of state maps. Suppose we pick a set of state maps And they satisfy the same desiderata as the classical case: normalization, linearity, positivity, and we require that this way of defining a norm is a C-star norm. In particular, these automatically imply that under complex conjugation, we get a reversal inside of state maps, and more generally, that the star operation is product reversing. If we include limit points of Cauchy sequences under this norm, we get a non-commutative C-star algebra, and that means we get a Hilbert-space from the genus construction. With this dictionary between, on the left-hand side, state maps and the C-star algebra, and on the right-hand side, the given Hilbert-space picture that has been generated. And this slide just shows that in the special case in which the projector we're asking about is rank 1, well, then this formula just spits out the usual Born rule. You can also show that if your given state map omega happens to assign a trivial probability distribution to a particular ontic random variable, well, then a simple calculation shows that the corresponding state vector obeys the eigenvector eigenvalue length. They come out automatically. Automorphisms of the C-star algebra that preserve all probabilities, these are information conserving transformations on the C-star algebra, correspond, there's a theorem, correspond to unitary transformations on the Hilbert space. So if our C-star algebra of quantum random variables evolves via a smooth sequence of automorphisms with time, that's equivalent to unitary evolution of the Hilbert space. If Stone's theorem applies, if you have a system of finitely many degrees of freedom obeying Heisenberg commutation relations or somewhat more rigorously Weil commutation relations, well, with some other assumptions, you get the Schrodinger equation for some Hamiltonian H. And moreover, that representation is unique up to unitary equivalence. But I'm going to take a step farther because there's a lot of dispute over how general that idea is. Is it generalized beyond non-relativistic systems of finite many degrees of freedom? And here, regarding Hilbert spaces, even C-star algebras as not fundamental, but just as mathematical contrivances helps us. Because we're not putting our ontology in there, it's okay if our Hilbert spaces and C-star algebras are not fundamental. So in the language of, are you an algebraic imperialist? This is Ara Georgis's formulation. Do you take algebras to be fundamental, or you're a Hilbert space conservative? Neither. Neither of them are where the ontology lives. They're both software layers. And this gives us some additional freedom. In particular, Fell's theorem has a profound impact here. So Fell's theorem says that if omega is any state map for a C-star algebra and you have any finite collection of elements of that C-star algebra, then if you're given any faithful Hilbert space representation coming from some, any faithful Hilbert space representation, there will be, with corresponding operators corresponding to the ones that you're talking about. Then for any epsilon, any positive epsilon, that Hilbert space representation will have a density operator that will give measurement results, predictions that are accurate to within epsilon for all I. Now, keep in mind, n could be the 1000th busy beaver number raised to the power of a googolplex. It doesn't have to be a computable number. It could be something insanely big. Epsilon could then be 1 over n. So there's just no empirical way that you are ever going to distinguish between two faithful Hilbert space representations, even if they don't have the fundamental property of traditional unitary twist equivalence. And even if one of those representations has parochial observables, certain limiting observables that aren't in the other, you can make n as big as you want. You're never going to be able to tell the difference between them. Now, if you take Hilbert spaces as fundamental, then you have this problem of which one is fundamental. But from our standpoint, Hilbert spaces are just fictions. They're just mathematical conveniences. You pick whichever one you want. You could think of the different choices of Hilbert space representations. As long as they're faithful, it's just different gauge choices. You pick whichever one is sufficient for the purpose at hand. We can see right away that there's going to be problems for joint probabilities, right? We know that if you stick in a single projector for corresponding to one outcome, corresponding to one ontic random variable, you get the corresponding probability. But in general, projectors don't commute anymore. If you recall back, we talked about set theoretic intersections having to commute. And this corresponded to classical projectors having to commute. Well, these projectors in general don't commute. And that means that if you attempt to plug in a product of two projectors for two incompatible observables into a state map, in general, you get a complex number. So this can't possibly be a probability. You can't even fix it by taking absolute values. That will screw up marginalization rules. You can't try to redefine it in some clever way because you won't be guaranteed to get non-negative probabilities. Quantum mechanics is screaming at us that even forgetting anything else that's in this talk, these are things you can plug into state maps. These are questions that simply do not have probabilities associated with them. This is screaming at us that probabilities just don't always exist. This just is the more general statement of this for more general outcomes. So the door is just open. The door has been kicked open to the notion that joint probabilities can simply fail to exist, and I would argue objectively as a fact of the matter. In the Platonic interpretation, this is extended, not just to incompatible observables, but anytime you have a bipartite system, a composite system, where the overall state map is not separable. And again, this will feature prominently when we talk about the measurement process. Separability, however, emerges naturally under decoherence, environment-induced decoherence, for example, during the measurement process. This renders state maps for joint systems over the relevant observables separable, and that's when joint probabilities approximately emerge, and we get to a very good approximation, correlations between the underlying ontic properties. This emergence, however, is epistemic, not ontic. It's not that the ontic properties didn't have values beforehand, it's just they didn't line up in a statistically correlated way until after this step. Let's talk now about the classical measurement process as a setup to the quantum process. So what we have is a subject system, which I'm going to model super simply as just having one observable A with underlying values labeled by little a measuring device D, this is our pointer variable, and an environment E. Initially, the measuring device has some known value. The pointer variable D is labeled by D naught, it has some particular specific value. The environment also has, we'll assume, some known value, pre-measurement value. Neither of these systems know the underlying value of the thing to be measured, A, of the subject system. So they would assign a non-trivial state map to it with some probability distribution over the possibilities. P of A is the probability distribution, and omega little a corresponds to being a trivial distribution that assigns unit probability to just that one outcome little a. There's some positive entropy associated with this. This is just the standard Shannon entropy that characterizes how much information currently is missing that the apparatus and the environment lack. The overall state map is factorizable. It's uncorrelated. There's no correlation between environment or pointer variable or subject system. Well, then the measuring device goes in, measures the value of A. Well, now the overall state map has classical correlation. The environment is still trivial, unit probability of being E naught, but the combined system AD, A subject system, D pointer variable, has a non-trivial state map. And that non-trivial state map is correlated. This is a standardly correlated state map. The probability coefficient is the same under an ideal measurement. This is classical. So even though the overall state map is not factorizable, it's a sum of factorizable terms. Classically, that's always true. There is a growth in correlational entropy. You could calculate the new entropy of the pointer variable and also the combined pointer variable and subject system, and they've both grown to equal the original entropy of the systems measured. And we interpret this as information has been communicated from the subject system into the apparatus. The environment then quickly joins the classical correlation. Now we have a sum over triply factorizable terms, and the environment grows to have the same correlation. The measuring device initially has an insider view. I mean, initially, after it does its measurement, I'm sorry, before the environment jumps in, the measurement device has an insider view. After the measurement device has correlated with the subject system's underlying variable, it now knows that specific underlying value. If there were a passive observer, so we're setting up here a Wigner's friend type setup. Wigner's friend is the measuring device. Wigner is this passive observer who has not talked to anybody, has not intervened, has not looked into what's been going on. The outsider view does not know the underlying value of A. The insider view, Wigner's friend, would now use a trivial state map because Wigner's friend knows the outcome, knows that it was little a. The outsider view wouldn't. The outsider view is still going to use the old state map because the outsider view has not learned any new information yet. So we see right away that the state maps here are perspectival classically. Okay? And in particular, we also see that the insider view sees collapse, but the collapse is not a physical process. It's a subjective process of updating based on the new information. And it's, again, perspectival, but not ontologically perspectival. The subject system always had that value before it was looked at. All the systems always had their values, although those values have changed, maybe. Certainly the pointer variable has changed. But now Wigner's friend, the measuring device, when I think of it that way, would naturally use a different state map from Wigner. That said, these two state maps, despite being different, they do agree the level of an ensemble average. If the outside observer, Wigner, considers all the possible outcomes, evolves them all with time, and averages them using the overall uncollapsed state map, that should be compatible with the particular evolution seen by Wigner's friend who got a particular outcome. There should be a compatibility level of ensemble averages. All right, well, now let's do the quantum case. Here I have a quotation from Asher Perez. Quantum phenomena do not occur in a Hilbert-space, they occur in a laboratory. That's where we'll see this happen. Okay, so similar setup, subject system A, measuring device, pointer variable D, environment E. Again, initially, the measuring device does not know the value of whatever it wants to measure, but the subject system, it's got some initial value labeled by D naught, environment labeled by E naught. In this case, to make it a quantum story, I'm going to assume a state map whose Hilbert-space representative state vector would be a quantum superposition over possibilities with square probabilities. The overall state map is initially factorizable, uncorrelated. The measuring device now goes in and measures the underlying value of A. Now the overall state map has direct entanglement between A and D. This is new. This did not happen in the classical case. This is known by some as a pre-measurement, which is sort of funny because the measurement has already begun to happen, but it's called pre-measurement anyway. We have a factorizable overall state map for environment and then the subject plus the pointer variable system, but the subject plus pointer variable system is not factorizable. And in particular, that state map is still pure. It's given by a single state vector, it's of this form. Okay. Now note, the entropy at this point of the subject system and the pointer variable is actually 0. That was not true in the classical case. The classical case, after this step, the entropy grew. Information was communicated from the subject system to the apparatus. Here, the entropy is still 0, which already makes me very suspicious that we should think that information has actually yet been transmitted and correlations have yet been introduced. And in the Platonic interpretation, it says don't assume. Yes, there's entanglement. Yes, that entanglement predicts that ultimately there should be some correlation, but at this point, no. At this point, the pointer variable and the subject system's ontic variable, they do not necessarily have correlated underlying ontic values, even though there's entanglement. But now the environment jumps in, gets entangled everything, and now when we trace out the environment to look at the decoherence going on between the subject system and the pointer variable, now the state map for that bipartite system, subject system and apparatus, now it has a separable form, just like in the classical case. And if you compute the correlational entropy, now it will agree with the classical case. So the Platonic interpretation says this is the moment when correlation has been established. Information has been transmitted, things have lined up, the students have compared notes and gotten their answers lined up. Okay, after the decoherence step, which is a physical step that actually can make ontic variables move around, maybe. And this is the famous step at which the non-locality jumps in, and I'm biting the bullet at non-locality. Non-locality happens at this step, but this is where it jumps in. Okay? And I'm personally not persuaded that any other interpretation does away with non-locality, but that's obviously up for debate. Now, many of the more serious no-go theorems, Cauchy-Specker, PBR, and so forth, they don't attach. They don't attach because they assume, crucially, that you have entanglement and you have joint probabilities at the same time. But we don't assume that. That's not assumed. Mm-hmm. And so the Platonic interpretation neatly evades all of those no-go theorems. GHC, it avoids all of them. However, this rules out, like, the theory is inconsistent. It doesn't rule out non-locality. And the GHC no-go theorem, the implication that there's non-locality going on, that part still attaches. But at least we don't get like a fundamental ontological paradox. We do, however, still get some non-locality. Measuring device, again, has the insider view. It knows the specific underlying value. Passive observer, Wigner on the outside doesn't, same as the classical case. This is identical to the classical case. Insider view uses the trivial map, knows the outcome. Outsider view uses a decoherent state map because the environment has come in, although the outsider doesn't know the specific results. The outsider is going to use a classical looking decoherent overall state map to make future predictions. And thanks to decoherence, these two state maps will be compatible at the level of a suitable ensemble average, as in the classical case. So quantum state maps collapse, but decoherence is separate from this. The decoherence process was physical. It moved ontic things around and established correlations. But the step of replacing The old state map with the new one after the decoherence process by the inside observer, that's a subjective change. The observer knows the final results and is going to use that and use the rules of quantum mechanics to predict future evolution of the system from that point. I would argue this is actually implicit when you take a branch by branch point of view in the Everettian approach after measurements, that each newly branched post-measured observer is going to use a subjectively updated state map in a similar way. And also it's explicitly done in the Bohmian approach, where we explicitly update state wave functions based on measurement outcomes. But we know that the person who gets the result is going to see a different wave function from someone on the outside. Okay. So according to Platonic interpretation, decoherence again is a physical process. It actually realigns ontic properties, but collapses subjective epistemic conditionalization that lets the insider make better informed predictions using whatever dynamical rule is then most appropriate for further evolution. Schrodinger equation, master equation, semi-classical methods. And again, I would argue that a similar subjective update of state maps for post-measurement observers is a feature of other interpretations. This isn't actually new, I would argue. According to Platonic interpretation, Schrodinger's cat is always ontologically dead or alive. We pick our ontic variables to be, particles, locations with a particular configuration. And that means there's an ontic fact of matter at every moment about whether Schrodinger's cat is dead or alive. Opening the box allows the environment to decohere everything and allows us to see what the answer is, but it doesn't make Schrodinger's cat jump from being a superposition of alive and dead to one or the other. So here's the conclusion. I'm just about out of time. This is a quotation from Aesop that I particularly am fond of. Beware lest you lose the substance by grasping at the shadow. The shadow here, I would argue, is Hilbert-space pictures or even C-star algebras. The substance is the underlying ontology. So each quantum system, according to this approach, has an ontology, has an ontic state consisting of ontic properties. And this is what probabilities are probabilities of. There's a thing for probabilities to be probabilities of. It could be positions momentous for mechanical systems of particles, local intensities, rates of change for field theory. There's also an epistemology, an epistemic state consisting of the degree to which those underlying values are manifest in the external world, encoded in individual probability distributions and their relationships. These ontic and epistemic ingredients follow complicated but ultimately summarizable nomology, a set of rules and laws. We can encode all these ontic properties, their individual probability distributions as ontic random variables, and we can codify all the individual probability distributions, their detailed interdependencies, their rules, all of this into a set of state maps chosen empirically for the given quantum system for empirical adequacy, which then determines a C-star algebraic structure, maybe not a unique one, but doesn't have to be unique, on the set of ontic random variables. That original choice has to be such that it generates an empirically adequate C-star algebra. And then we can talk about when it is that joint probability distributions exist. They exist in these special circumstances. And in particular, this novel ingredient that they don't yet exist when there's entanglement, not until the state map is separable. So given a C-star algebra and a set of state maps for a system, where the set of state maps actually determines the structure, the algebraic structure of the resulting C-star algebra, the genus construction automatically spits out a Hilbert-space picture, which we then see as a useful software layer. There's no need to reify it or attach a direct meaning to wave functions, just like we shouldn't read too much into classical canonically transformed phase space variables, Hamilton's principal functions, symplectic manifolds, non-commuting Kutman von Neumann operators, and so forth. And then there's the obligatory quotation from Korzybski. A map is not the territory it represents, but if correct, has a similar structure to the territory which it counts for. This is not confusing the map with the territory, which was, I think, also part of the motivation, the inspiration for René Magritte's, famous pipe. Great. So, are there hidden variables here? Well, ontic properties are the starting ingredients. I'm not supplementing an existing Hilbert-space picture that I'm taking seriously and regarding as physical and ontological with additional ingredients. I'm doing what I do classically. We have some ontic properties. Newton says, oh, there's some particles floating around, that's my ontology. I'm going to layer mathematics on top of it. I'm going to layer on calculus and vector functions and differential equations and use these to make predictions. But then you don't go back and say, well, now I guess the original particles are just hidden variables. I mean, no. The hidden variables are all that's really there, and the patterns of their behavior. So going back to that sequence of numbers, there's ontic variables, ontic properties, and they exhibit patterns of behavior, statistical patterns of behavior. And that's what's there. And everything else is just convenient mathematical layering that lets us make predictions and formulate and work with these things in a convenient way. So from this point of view, it's the Hilbert-space pictures, unobservable wave functions, linear operators, and so forth. Those are the hidden variables. There's no Heisenberg cut. There's no special parameters like in spontaneous collapse approaches. And there's actually no modification to textbook quantum dynamics. This actually validates a lot of the stuff we talk about. We talk about, oh yeah, there's a particle and it's fluctuating and we don't know what its position momenta or whatever. That way we talk is actually validated to some degree by this approach. There's no privilege status for agents at all. What does it mean for a system to be a measurement device? It just has to be able to correlate with a pointer variable with the thing being measured. It's got to be big enough that you get good, robust decoherence. There's nothing else special that measurement devices have to have. There's no need to reify Everettian branches. There's no need for ad hoc guiding equations. After measurement, you just use quantum mechanics to predict what the system's going to do. If it's a big classical type system, well, then semi-classical method is going to give you very good predictions about the average behavior of the underlying ontic variables. But in particular, and this is crucial, there's no need to derive an ontology from the configuration space, from the domain that wave functions live on. This is important because if you just take a flat-footed attitude toward fermionic field theories, to the extent they have wave functions, they're wave functions defined on a Grassmann anti-commuting set of variables. And that's really tricky for talking about Bohmian type approaches, trying to derive an ontology from them. Here, not a problem at all. Fermionic field operators anti-commute, fine. But that anti-commuting is just a statement about their epistemic-nomic behavior. Fundamentally, fermionic fields have real or complex values like bosonic fields do. The fact that there's no eigenstates for them, mutual eigenstates for all the field operators, there's no wave functions is completely immaterial. In this point of view, we can assign fermionic fields local numerical values just like bosonic fields. After all, their expectation values are not Grassmann numbers. Their expectation values are real or complex numbers, just like they are for bosonic fields. And so this just eliminates a huge source of problem for certain approaches. And that's it. Thank you.